Everyone, my name is Taylor Sparks. I'm the editor-in-chief of Integrating Materials in Manufacturing Innovation, and we've got a new paper to talk about. It comes to us from Sandia National Laboratories. The lead author is Aashique Rezwan. Now, this paper has all to do with quantifying microstructures of additively manufactured components, and they're going to use a new tool here. They're going to use spatial statistics. The paper begins talking about one of the key challenges that we care about microstructure. Obviously, that's where things like porosity, cracks, dislocations, inclusions show up, and those definitely impact performance. But microstructure is not always deterministic. It has a stochastic or a random nature to it. The same process a bunch of different times will give you slightly different variations of a similar microstructure, right? That's a challenge. It says right here, even nominally identical materials or parts will exhibit subtle differences in their microstructures. And so statistical approaches, things like spatial correlation functions, orientation distribution functions, grain size distributions, these have been used for a long time as a sort of robust framework for analyzing and comparing microstructures. In fact, they point out some foundational work. Check this one out. Take this one. This is an annual reviews of material science paper that goes clear back to 2002, where Torquato talks about some of these different statistical descriptions of microstructures that can be used to quantify the microstructure. Now, while these distributions are straightforward to use, it says they don't tell the whole story. It says they were developed for manual measurements performed on analog instruments. They don't take advantage of the data-rich outputs of these sort of state-of-the-art characterization methods or their digital nature. So there could be some improvements to be done. They point out a couple. One is generalized spherical harmonics, right? This is a really useful tool for capturing crystallographic symmetry and crystallographic orientations and quantifying those, right? Or the Euclidean distance transform, right? What this one does, it creates a distance map of the features in the image. Things like grain boundary maps, for example, could be generated. These are two just examples of tools that could be used. The underlying hypothesis of this paper is that they're going to use these tools in conjunction with a feature reduction step and then a machine learning step to try and capture differences that wouldn't be obvious to the human eye. So obviously they're going to be doing this on real parts. Here they have a Pro XDM P200 machine that's going to go about doing the laser powder bed fusion on their 316 still. Here's an example of the types of printed samples that they're coming up with, right? Clearly they are varying the orientation of the samples, right? And the three different builds themselves are going to be distinct as well. So this is a figure that's showing the basic workflow of what they're going to do. They're going to take and do actual microstructure characterization. They're going to extract features out of that using these spatial statistics tools, both EDT and GSH. Then they're going to pass those through this feature extractor. This is a variational autoencoder. It's basically going to reduce the dimensions down for them such that when they do this dimensional reduction, they can plot this lower dimensional space and see whether or not clustering is able to find things that should be in common with one another as opposed to things that aren't in common with one another. So the good news is that this actually works really well. Take a look at this figure. Comparing A and B, A is the reduced dimension, right? This is using EDT data, right? So that's the spatial statistics they're using here. And it's able to clearly cluster three different examples which correspond to the three different build plates. Very, very cool. However, it is not able to very effectively cluster things that have sample orientation accounted for. For example, take the green dots here. Those are all oriented the same way. Or the black dots are oriented the same way. They are not showing up as distinct clustering, right? And that sort of makes sense because EDT doesn't take into account this EBSD data where you'd be ideally learning about that. Meanwhile, if you now take that same sort of analysis, but instead of using EDT as the spatial statistics, you're using GSH data, it's able to differentiate between different build plates very effectively, and it's also able to differentiate between orientations where you're able to actually see different clusters forming by orientation as well. And then one of the cool things I found about this is they're also able to use this to identify outliers. There's clearly this blue data point is an outlier here. They were able to look at that microstructure and observe, oh yeah, okay, that one had a bunch of porous, nature to its microstructure that was distinct from the rest of the samples in the batch. So what's the takeaway here? They've got two new cool spatial statistics that can be leveraged, right? EDT and GSH, and they have a way of reducing that dimensionality in a way that makes it easy to extract information from those and put it into a pipeline for characterizing materials. I hope you'll take a look at it in the latest issue of IMMI.